first, let's just try to recall what we learned last week. So last week we were staying at the parts probability. So there we introduced some concepts and terminologies. So like the laws of set theory and the axioms of probability, particularly for those rules like multiplication Bayes rule and the law of total probability. Let's just quickly go through it first. So first of all, we lead three concepts: sample space, event, and experiment. Yeah, so here for sample space, yeah, we may consider a subset of it. We call it a event. Yeah, so here, remember, event, mathematically, it corresponds to a set. When we mention event, we just want to consider some randomness. But when we mention set, we just know that it would be a kind of set, right? And then here we have three operations for set or just like event, right? Yeah, set or event, union, and interaction, and next one, like complement. For complement, you use A prime or just A C, or sometimes you use A bar. So each of them just means the whole sample space and deduct the original set A. Yeah, and then empty sets, so that means they do not have the common element. Yeah, and then here we have two words like mutually exclusive or disjoint. Yeah, these two words we use to describe the relationship between two sets or just like two events. Here is some laws of set theory. I do not mention much. Yeah, just like plus, minus, or like the quotient, right? Yeah, the quotient, sum, yeah. And then we introduce very important, I call it cornerstone of the data science, axioms of probability. So 概率公理. So here we just know that, first of all, the probability is a possibility. So it is a value if we try to measure by the measurement P, probability. So it should be a value between 0 and 1. And over the whole sample space, the probability is almost surely. And then if we have finite or infinite sequence of mutually exclusive events, then here the union just becomes plus plus, right? Under such a probability measure calculation, okay? So this is something we learned. And here we have some properties that we use often from 1 to 7. Yeah, here we have many things, right? Yeah. So next one, results with conditional probability. Yeah, this is extremely important. And meanwhile means what? It is a bit of complicated, and we will see what it is. So first of all, definition of conditional probability. So here we have probability of event A given or conditional on event B, right? So this is the conditional probability we try to say, and then we know that it would be a quotient. For this quotient, it is the intersection and then over probability of the marginal B, right? So this is the conditional probability. Based on it, we then have three very important rules. Number one, we call it the multiplication rule. That is, here you actually move the denominator to the left hand, and then you go out to have a formula here, right? So this is a multiplication rule. And then next one, here you would notice Bayes rule. So for this Bayes rule, we say this is pretty important, particularly under data science, under machine learning. Yeah, here, separately, you can write marginal P of B, or just like P of A. But then that means what? That means here you actually have such a marginal multiplied by conditional, right? So here you have such a relationship, and then if you try to, for example, if you try to move PA, and then if you try to move this one to the other side, then you have this Bayes law, right? So we call this one form. And also here we have a multiple form, right? Yeah. Here, if you have BR, and here, attention, your BR mutually exclusive, we say a partition of S. We call it partition because the elements mutually exclusive. So in this way, we don't have such a right now we use so many such Bayesian spirits, Bayesian approaches, Bayesian idea, etc. Yeah. So this is one that we have, rule 2. So rule 2 Bayes rule, is actually also based on the definition here, right? Yeah. We say definition of conditional probability. So number 1, multiplication, number 2, Bayes. Also, we have the number 3, the law of total probability. So for this law of total probability, if we try to do something, so it means PA equals PA intersection S, and then it equal to PA intersection, and then inside you actually have BI, I run from, for example, 1 to M or possibly infinity, whatever. Yeah, so you have this one, right? So this is way. And then next one, you just have A intersection N in BI. Yeah. So here excuse me. Here you can see you have A intersection L in BI. Yeah, intersection. And then for the plus, yeah, attention here, A intersection BI denoted by ABI. So every ABI just belongs to what? Belongs to BI. Therefore, here becomes plus, 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 right? Mathematically, you can quickly derive it. So this is the law of total probability. These 3 probability properties are extremely important. Keep it in your mind, and then you can derive many things. For example, today later, we will introduce the functional form about it. Yeah, so this is something we learned last week. And last week, I also mentioned random variable. Here we have such a concept. Random variable. What's the concept then? Here, for this concept, we said it is a real valued function. It defined on a sample space and then with a probability measure. So if we try to show, so that means x of omega, and then here is defined on a sample space with a probability measure, and then here would be the real line, right? So random variable. So here, attention, omega is an element from the sample space, one outcome, right? So random variable, remember, you actually do what? You do some abbreviation x instead of x of omega. So this one that we have. And next one, just like the CDF. So here CDF, according to the definition, it would be the probability bounded by an argument x, lowercase x. So this is the CDF function. And if you learn survival analysis, you know there would be another one, Sx of x. So for this one, we just denote by what? Probability x greater than lowercase x. Survival probability function, you see? See that? So that's why you see here for distribution function, yeah, we have many, right? Yeah, we have the distribution function. So for such kind of a distribution function, you have many ways. You may by less than or equal to, or you may use greater than. whatever, it is just a value between 0 and 1, right? 0 to 1. Yeah, this is our CDF. And next one for CDF, usually if you define a CDF, it has some property, increasing, and on one end, yeah, is on one end equal to 1, the other end equal to 0, and also right continuous. But sometimes people may use x minus 0. That is a left continuous. Yeah, you choose any of them, but we don't care about that. Yeah, remember, for this course, 2 parts are important. One is about my lecture. So you see, each time I will prepare you some documents, majoring you using our textbook. But meanwhile, I would add some supplementary document to show you. So from my aspects, I hope you guys to understand a broad scope of knowledge. You understand what it is, roughly what's that? And then the other key part is our tutorial. Yeah, you see, through tutorial, you will learn tutorial question, and those questions will help you to handle your assignment, your midterm, your final examination. And through your tutorial, you may use it to solve your mini projects, group projects, right? Yeah, so both parts are important. But if you ask me a question, what on earth, which one should I choose, the lecture or tutorial? If you have to choose one, I would recommend you to my 2 PhD students, our tutors. Why? Yeah, you see, over there, you learn some practical things. For example, today, the other tutor, Miss Lin Xiaoli. So Lin Xiao will teach you like how to generate a random number, how to like have maximum likelihood estimation, how to have the confidence interval. You have to learn that through Python. And in our midterm or final examination, the question would be in this way. I show you some code, right? Open book. So I show you code, and then you have to know how to read the code, how to read the results, and then answer the question. Get that? So tutorials are important. Not miss that. But for my lecture, it's all right. Yeah, even you forget it, you skip that, I guess you can go back to the hard copy, right? And then pick up. Okay, so go back here. Here is the random variable. By far, we review everything. And today we go to some new things. The first one, I want to introduce discrete random variable. So for discrete random variable, it means what? It means that a random variable take on finite or countable infinite possible values. Yeah, for example, if you say you just throw a dice, so the possible outcomes would be 6, right? 1, 2, 3, 4, 5, 6. Yeah, so finite outcomes. Yeah, but if you say you have to, you queue in a bank, so you see how long will you wait until your service, and then if you count the minutes, 1 minute, 2 minutes, and then if you use minutes, it can still be countable, right? Usually at 5 p.m., the bank will be dismissed. Yeah, so if you count minutes, it works. But in some other situation, I mean, ideally, when you try to model, you say the countable infinite. Yeah. So here for probability mass function PMF, let us you define a mass. Yeah, on a point A, here you have a mass. So yeah, you can denote by probability of the event or just by PXA. So for this one, you know it also satisfies properties like other place only 0, and it should be non-negative, summation would be 1. And also here you have the CDF. For this CDF, immediately you can see we have some summation, right? Summation of what? Summation, attention, here is a bound. So for every value, when you try to have, so this one should be bounded by your lowercase x. So you have the aggregation of it, right? So This one just shows you how you get your CDF. Yeah, get that? PDF, CDF. For examples, if you want to do it, you can do and ask me for solution, okay? But if you say, I do not want to do that, that's okay. So this is about a discrete random variable. Next one, we go to the continuous situation. For continuous random variable, you can see we actually use what? We use a integration over a region. So here for B, you may say this is an event, a set. You may also say it could be a region, right? So over this region, you do some integration. And for this integrand, so this is your PDF. Yeah, so this one would be probability density function. Yeah, so this is your PDF, right? Continuous random variable, we have it. Yeah, and if you try to write it, yeah, remember here we use a footnote X to denote the random variable. And also it has property greater than or equal to 0 and over the whole real line. Yeah, you see, you may write in this way, fx x. So this one would be exactly 1. Over the real line, the integration would be 1. Yeah. And then we have the cumulative distribution. So for this cumulative distribution, attention, you have x. So your x appears here. See? We call this one, I don't know what's the English name, 不定积分. Yeah, because here x is an argument, not a constant, right? So we call this one some 不定积分, okay? So here, attention, so when you try to write this, attention, for this place, you can only use a t, not use x. See that? Attention, this place. Yeah, when you try to write some mathematical thing, you make sure you write precisely. So this is our CDF. And this one tells us all possible statements about x can be answered in terms of f. Not only f, here, I mean, for this, in terms of f, we can replace by capital F. We can also replace by survival. And later you can see we can replace by hazard, replace by MGF. That means what? For any single random variable, then if you consider any format of its distribution, yeah, they are one-to-one. So you may use CDF, survival probability, hazard, MGF, and even like a characteristic function or so forth, okay? And also one property is about what? On a fixed point, the probability would be 0. See? Why? Because it is continuous. It is continuous. That means what? That means if you try to zoom in, yeah, and then you can see it never be break. It never be broken, okay? So here, on a point, the probability would be 0. But remember, for the above, here we just said, yeah, other place except the xi value, so it takes value 0, right? Yeah, but here it just tells you because it's continuous, so on a fixed point, the probability must be 0, okay? And next one, differentiable. So here CDF, after you do some differentiation, it would be your PDF, right? So this is something you learned. Okay, here is a question you may try, yeah. Next one, I want to introduce the mixed random variable. So here for this mixed random variable, when we mention that, we say that it combines, yeah, mixed. If the distribution function is not a step function, but discontinuous at some point, right? Yeah, there would be some discontinuous points, so you don't have the mixed random variable. So in such a way, you just see, if you try to denote such a CDF, so this one would be a linear compilation, right? So we have such a linear compilation. And for this linear compilation, it has two weight, 1 minus k and k, the weight, right? And their summation is 1. So this is the mixed random variable. And also I want to introduce you guys about some mixed distribution. Mixed distribution. So for mixed distribution, one is very famous. You can guess what's that? Gaussian. Gaussian mixture distribution. Yeah. So yeah, Gaussian mixture distribution. Yeah. For Gaussian mixture distribution, what does it mean? That is, if you have a normal, yeah, this is a normal distribution, right? And this one, you notice that it is a mixture, like it's, yeah, mu2 or mu alpha, sigma alpha square alpha plus 1 minus alpha. And then this place, you just write normal distribution, mu 1 minus alpha, sigma square 1 minus alpha. Yeah. Yeah, you see, sometimes if it's normal, it works well. Not normal, you may notice that through log, it could be normal, or through exponential, it can be normal. And the third way, just like for a normal distribution, it can be what? It can be the linear combination of two, alpha 1 minus alpha. So their summation would be a Gaussian mixture. Gaussian mixture distribution is really important. If you guys go to Bishop's book, Pattern Recognition and Machine Learning, so there it has a full chapter to introduce. Yeah. So this is one thing I want to introduce here. The next one, I want to introduce the concept moments. So for moments, so you would come the question, why? Why do we learn moments? Yeah, as we mentioned, if you know any distributional function of a random variable, then you can solve everything. Unfortunately, many situations you do not know the distribution. So you see, perhaps I can get some features, right? So what kind of features we care? For a random variable, the moments are extremely important features. For example, we first introduced the concept, the Arth law moment. For the Arth law moment, that means you have E of XR. For example, here EX. So this is the mean value, right? So mean tells you central tendency, important. And here, when you calculate such kind of Arth law moment, for discrete case, you use the summation. For continuous case, so you use the integration. But inside here, attention, you must have the XJR or XR, and then multiplied by what? By the probability density. See, so be careful about this one. Okay, so this one is about Arth law moments. Next one, the Arth central moment. Arth central moment. So for this one here, you can say X minus mu with power R. So here, for example, for mu2, you know, this is exactly our variance. So variance tells you variation is quite important, right? As I introduced in the first lecture, in data science or in any situation, people care about variance very much. For example, like if you ask me, Catherine, how old are you? So if my answer is, oh, my age is between 8 to 80. So this variation is too large, right? You have low information. So that tells what? You cannot tell how old I am. Yeah, but I just tell you, oh, my age is between 35 to 45. So here, 35 to 45, the range would be 10. So this one much smaller, you then can guess, right? At most, you can guess 10 times, you know the answer, right? So the variation is more, information is more concentrated. So that's why for variance, it is a very important measurement, whatever for statistic or for data science. In statistic, variance could be some efficiency symbol or just like some relative efficiency. Yeah, like you may heard that. And the feature information, you may heard that, right? Feature information important. Yeah, each time we try to measure the information. So variance actually tells you such information. Besides variance, sometimes people consider the inverse of some variance. Yeah, how do we understand that? Yeah, for example, if you consider you have a x1, xm, yeah. So if we denote this one by a x, okay? So this is m by 1, right? So if we have such a vector, for such a vector, and if you calculate its covariance x, yeah. If we want to calculate such kind of covariance, what would it be? So this one, you know, is actually the variance of x. You see? Variance of the vector would be covariance. And then this one would be what? Yeah. Like, the covariance x1, x1. The covariance xm, xm. Oh, pardon me. Right? So this is around the diagonal. Of the diagonal, you have covariance xi, xj. Well, similarly, this place also, right? So this is m by m, or you may write it by what? Sigma ij, m by m. And here sigma ij would be the covariance xi, xj, right? So this is how we have it. Then we call this one the covariance matrix. Yeah. So for such a matrix, if you consider its inverse, we call this one the precision matrix. So why do we use such a name to define inverse of the covariance matrix? The reason is, you know, if you have estimator, okay, yeah, like estimator, everybody, I suppose you know that. Then estimator just means some approximation to a real thing. You don't know what it is, right? And then if you consider like estimator and the real thing, their deviation, yeah. If such deviation very small, so that means the estimator close to the real one. So we say it is accurate. Yeah. But if we just try to see the variance of the random variable or an estimator, so we hope that such variance could be as small as it can. When it's smaller, we say the estimation is more precise, right? For example, you have a confidence interval. Usually the confidence interval, if the range or the length of the interval, yeah, you may say the width, the length of a confidence interval. Yeah, maybe I just try it here. Yeah, confidence interval. Yeah, if you have a confidence interval, so that means here, for example, here is a T1x, and here is a T2x. Yeah, if this is your confidence interval, right? So then here for T2x and then minus T1x. So this one, we call it the length or width. Yeah, it could be a length or width, right? So smaller, then more precise, right? And then this one measures the variation. And also like here, for variance of x, here is the inverse. So we call it a precision matrix. Because from the elements inside, you can see how your estimation would be, or how your variation of x would be. So the inverse called precision matrix. Yeah, this is one thing we want to introduce. Next one, we want to introduce the shape parameter. For shape parameter, here we have two things. The first one, skewness. So here, skewness of a distribution, we use alpha 3 to denote. So this one tells you if greater than 0, I mean, here alpha 3 would be what? Would it be the power 3 with a divisor sigma 3. So if this value greater than 0, the distribution skewed to the right. Yeah, this one just skewed to the right. Yeah, so we call this one the coefficient of skewness, or we just call it asymmetry. Yeah, so this is one thing, skewness measures the asymmetry. You know, for normal distribution is symmetric, but it might not be normally distributed. So people would to measure how the asymmetry would be. The next one, kurtosis. For the kurtosis of a distribution, so this one actually measures the picketless or narrow Hubbard, yeah, of a distribution. So if it's less than 0, negative, right? So more packed than a normal distribution. So here, attention, when we mention skewness and kurtosis, we actually compare the distribution curve with whom? With the bell-shaped. You know, normal distribution, sometimes we say is bell-shaped. So here the shape parameter just measures compared to normal distribution, what happens? The skewness or kurtosis. So here it has another name, coefficient of kurtosis, or just the flatness. Yeah, this one that we have. Okay, next one, expectation. So expectation is very important concept. You guys must grasp it. You can see for those people who are doing in financial math, they use a lot of expectation calculation. So what does expectation define them? The expected value of x is called expectation. And for expectation, so here we can see for discrete situation, it would be the summation. For continuous situation, it would be integration, right? So this is the expectation. Yeah. Also called the mean of x, right? You use mu or mu x. Yeah, this is one way we have is expectation. Besides expectation, here we have more. For example, you can see if you consider expected value of a function gx, if here we have a function, we try to do that, okay? So here you can see for discrete case, we have the summation, and for continuous case, we have a integration. Yeah, this is one that we have expected value and the discrete continuous how we do. Here we have more properties. Yeah, like a constant can be taken out, plus can be plus. Yeah, so then for linear combination, it means it can be move out, this one move out, right? Yeah, so expectation and summation can be exchangeable. This one tells you, okay. Next one, here we have two, median and mode. Median I introduced last week. For median, if M is a median, that means less than and greater to, these two probability would be the same and also equals to 0.5, right? Yeah, this is a median. just means it's a real value less than or greater than half. Yeah, for example, for Hong Kong, yeah, if you consider like the family, like a family monthly average, if you use mean value, if you use mean value to calculate a family's monthly income, what would it be? Can you guess? So you may guess like 35,000. Yeah, that's a bit of high, right? 35,000, 35,000. Yeah. But if you look at the median value, you know what it is for families? Yeah, for families' monthly income. The median value? 18,000. Yeah, different, right? Why? The reason is obvious. In Hong Kong, the rich and the poor, here, the distance are too large. Yeah, in Hong Kong, the Gini coefficient is very high. Yeah, because some people are extremely rich, but some are very poor. Yeah. So if you use mean value, it tells you nothing. Seems like, yeah, high salary, we come here. But if you look at the median, so not very high. Yeah, but that's the truth. Half of Hong Kong people whose monthly, like the family income would be less than 18,000 and half would be greater than. Yeah. So median is important. It tells you some real fact. Okay. The other one is about mode. Mode is what? For mode, here we say it's the most likely value. For example, if you have several, one mode, two mode, three mode, yeah, seems like if you have several peaks, so there would be some mode value that appears very often. Yeah. So here is median and mode. Next one about the quantile. For quantile value, here I want to introduce you a concept here. Yeah, this way you may see it as a definition of quantile. Yeah, and then cosine p is our quantile value, right? Yeah, for example, you may write probability x less than 1.64, and this probability might be, I'm not sure. I'm not very sure whether it's this one. You may check. Yeah, you may check. I mean, if x follows a normal distribution, yeah, if this is a normal distribution, so you may have this, right? So here for 1.64, this is your cosine 0.95. Get it? So that's why we have such a cosine p, and then it's p. Probability x is bounded by cosine p, and then it would be exactly the p-value. Okay. So this is one that we have, the piece quantile. Yeah. So next concepts, attention. Here we say piece quantile. And next one I want to introduce is percentile. For percentile, attention, you have actual 100 coefficients before the piece quantile. See that? Yeah. So this one that we have piece quantile. And then, for example, like 40% percentile, 0.7 quantile, right? But attention, for such one, you cannot write in this way, cosine 50. This is not right. Why? Because here p just like a decimal. Yeah. So here p is only a decimal, like 0.5, 0.95, etc. Yeah. And also we have the piece sample quantile. For piece sample quantile, that means if you have order statistic, yeah, you see y1 until yn, so you try to find out k would be exactly p multiplied by n plus 1. See? So in this way, we then just know that it's the piece sample quantile. Yeah, that means you have some discrete ordered sequence, and then you just try to find out the middle one, right? Yeah, this is about the quantile. Next one, like some application of quantile, sample quantile. For this one, we want to introduce 3 things. Yeah, so look at the one here. Sample quantile, the first application, box plots. I suppose all of you know that, right? For box plots, why it is important? Because it tells you 5-number summary. 5-number summary. For example, you can find out the minimum value, the first quartile, median, the third quartile, and the maximum, right? We call it 5-number summary. Yeah, for example, my graduated PhD student, he has a quantile functional classifier. That is, if you have many curves and then you try to do some classification, how can you do that? So we have one method that is based on the quantile. And then we found that you use at most 4 to 5 the quantile curves, you then can classify the functional curves precisely. And for my another PhD student, his work is about how to build up a prior for some monotone increasing function. So in that way, he also used just some I-spline methods, and then let students use the quantile to characterize the I-spline, and also like 4 to 5 points, then you can do a very good prior. So then you can save a lot of time to tuning the parameter. So here, I just want to tell you box plots. The 5 summary are important because you actually use 3 quantiles there, the median, the first quartile, the third quartile, right? Yeah, this one good. Next one is about the QQ plot. QQ plot is also very famous, right? For QQ plot, this one is YK versus cosine ZK. So Z here is the standard normal. Yeah, so this one can detect deviation from the normality. And the third one, just like the normal QQ plot. So QQ plots using normal quantile are called normal QQ plots. But if you do not use normal, use other things, so it's QQ plot. Yeah, so these 3 are very useful. Next one, I want to introduce MGF. So MGF, in mainland China, when we learn probability, we do not have this one, right? Yeah, when I was an undergraduate, we do not learn this one. But when I read my PhD in Hong Kong U, so I started to learn it. Yeah, because I have to be a tutor there. So I learned MGF. So this was actually very useful. So what does it mean? That is, you try to use expectation and then exponent parts of Tx. Attention, for this inside, sometimes people write in this way, exponent parts T of X. Yeah, the first lecture we introduced this already, right? So if you do it this way, that means what? That means when you have such a expectation operator, so it would be the product of 2 terms, and then it could be what? It could be the summation or just like the integration for discrete or continuous case. Yeah. So what is the advantage for MGF? You can see when you use exponent parts, you actually make the value long-negative, right? So sometimes it seems like long-negative has more mathematical convenience. So that's why people use MGF. And also here, the other main reason people use MGF is what? If you make the orth moment, so here the orth moment can be obtained by a 2-step procedure. The first step, you do some, the first step, you do some derivative, the orthogonal derivative. And then the second step, you substitute 0 and 2. So then you can find that you actually have the orth moment, right? Yeah, so this one tells you for MGF mathematically convenient, so people can calculate the moments immediately. Yeah. And here, like, yeah, if you want to try, you can try this example. Yeah. Here I want to show you some property. For such properties, like if you have the plus, then it becomes what? It becomes a coefficient. And this coefficient would be what? Would be some exponent parts t, and then with the plus part here, right? Yeah, you plus a. So this one would be the one you have, plus. And then for the coefficient here, so this one just go to this place directly. And the third one, look at the third one, that means what? That you actually have x, b plus a plus b, right? So you combine the first two rows, then you see here is a plus b, here is the one here, right? So MGF, here some convenient calculation. And also I want to introduce the fourth property. If x and y are independent, in such situation, people use x and y independent. Yeah, people use such a thing to denote. And then you see the plus parts would be what? Would be the product. Yeah, this one just tells you when x is independent of y, we would have it, right? So this is one that we have. Here we have more. Yeah, like the PMF, we can have the things like it. Next one, I want to introduce some key function. Key function. Here I should say with respect to a random variable x. Yeah, I would like to repeat maybe the third time or the fourth time. For any random variable, if you know the distribution information, then you can decide everything, right? So now you can see here we have multiple choices. It could be CDF, that is f x of a, right? So this one would be what? This one would be probability x less than or bounded by a. So this is our CDF. And also we have PMF or PDF. And also we have MGF, like expectation, E as base, TX, right? And today I would introduce more survival probability function. So why do we call it survival probability distribution function? You can see for this SX, yeah, because it's still the probability measure, right? So even you write in this way, it would fall into the interval 0 to 1, right? So this one would be exactly 1 minus fx, right? Yeah, because this one is 1 minus probability capital X less than or equal to. So this is the one you have, right? So that's why sometimes people use CDF, sometimes people use survival function or survival probability function. And you may also use F bar to denote. Yeah, this is the way you have it. Next one, I want to introduce the hazard rate function. Hazard rate, 失效率, or failure rate, 风险率. Yeah, this one we call it 风险率, sometimes like 失效率. Yeah, in survival analysis, in medical health, people use hazard rates. In economics, people use failure rates. But whatever which environments in finance, econ, or just in like in medicine, the mathematical format is the same. That is, you either have such a hazard rate would be the quotient between what? Between your probability density against the survival, right? Or you can further have some formats like here, you replace by 1 minus CDF, or just like you may consider use the survival probability and its derivative, use a quotient. And even you can use this one directly, right? You have many ways, but whatever, Yeah, just remember, very originally, we just have the concept here. It should be a quotient between the probability density mass against what? Against the survival function. Yeah, so this is our hazard rate. And you may also further have the survival would be what? Would it be some function with respect to your hazard rate? Yeah, you see. So that's why they are 1-to-1. Yeah. Let's take a break, and then 30 we go back.